Welcome to the lecture series on differential equations for undergraduate students. Today's lecture is in continuation of Fourier series. In last lecture we had learned that for periodic functions we can find out the Fourier series of those functions. We had learned the method to find out the Fourier series for given functions. In the examples we had seen that for certain functions we were getting the Fourier series containing either only cosine terms or only sine terms. When it is happening, can we answer this? Yeah, we can answer it, but before that we will relook at certain properties of the function. So, first we will see even and odd functions. First, odd function. A function would be called odd if for f of minus x is same as minus of f of x for all x. Say for example, in this function, here we see this function is from 0 to 2. If we see the values are in the negative. So, let us see at the 1. At the 1 the value of this function is minus 1. Now, if I see value at minus 1, value at minus 1 is plus 1, that is minus of minus 1, that is plus 1. Similarly, if I see any value, let us say here at half or at 0.5, the value over here is coming somewhere here as 0.6 or something, and when we are moving here we would be getting this is in the negative and here in the positive one. So, we are getting is that this function is odd, that is it is changing its mode, whatever it is going upside the x axis, that is towards the positive y axis, the same thing is being repeated in the reverse order in the negative side of the x axis, or that is the y axis. Similarly, for even function, a function is called even if f of minus x is f of x for all x, that is it is not changing the sign. Let us see here, we see again here is the function which is something a triangle kind of thing on the positive side of x axis. If I go to the negative side of the x axis, we are getting the similar kind of function, that is if I see the value at plus 1, the value at plus 1 is somewhere here as actually the plus 1, and at minus 1 is also the value is plus 1. Similarly, if I see value at 2, value at 2 here is coming somewhere as 0.5, while as at minus 2 if I see the value is again coming as 0.5, that the value of at the positive side of the x axis whatever is we are getting is the fx, the same thing we are getting on the negative side of the x, that is the function is repeating itself on both the sides of the x axis. This is called the even function. So, what we had learned that any function fx would be called even if f of minus x is same as f of x for all x, and odd if f of minus x is same as minus of f of x for all x. What these properties are, what this even or odd is telling us. Let us see the three main facts for this section. First is that if gx is an even function, then if I integrate it over any interval from minus L to plus L, I can write it as 2 times integral 0 to L gx dx, and if gx is an odd function, then this integral minus L to plus L gx dx is 0. This we are knowing from the properties of the definite integral. The third property which we will be using here is the product of an even and odd function is odd. Now, let us see what is happening with this function in the Fourier series. So, the result here is the Fourier series of an even function of period 2L is a Fourier cosine series. So, that means we will get the series fx as a naught plus summation n is running from 1 to infinity a n cos n pi x by L, with the coefficients a naught as 1 by L 0 to L fx dx and coefficient a n as 2 by L 0 to L fx cos n pi x by L dx for n running from 1 to 3 and so on. We see here that the coefficients as such it was 1 upon 2L 0 to minus L to plus L fx dx a naught. Now, we are saying is that because it is an even function, so integral minus L to plus L fx dx is 2 times 0 to L fx dx. So, we are changing this integral from 0 to L only. Similarly, in the a n also the integral is being changed to 0 to L. Similarly, the Fourier series of an odd function of period 2l is a Fourier sine series. That is, I would get the series as fx as a naught plus a n sine n pi x by l, where a naught would be 0 and the coefficient a n would be 2 by l 0 to l fx sine n pi x over l dx. Now, since it is an odd function, we would get that fx integral with this fx and sine n x, the both are odd. So, product of odd and odd function would be even. So, this integral would be from minus L to plus L would change to 0 to L, while when we are writing fx into cos n pi x, that would be odd function and that would result as 0. So, next we are getting that the Fourier series of a one more property, the Fourier series of a sum function f1 plus f2 can be obtained from the Fourier series of functions of f1 and f2. What it says is, it simply says is that Fourier coefficients of the sum function f1 plus f2 will be the sum of corresponding coefficients of f1 plus f2. That means, if I do have a function f1 whose Fourier series is a naught plus summation n is running from 1 to infinity, a n cos n pi x by l plus b n sin n pi x by l, and another Fourier series for the function f2 as a naught star plus summation n is running from 1 to infinity, a n star cos n pi x by l plus b n star sin n pi by x over l. Then we will get the Fourier series for f1 plus f2 as a naught plus a naught star plus summation n is running from 1 to infinity. The coefficient of cos n pi x by l would be now a n plus a n star, plus the coefficient of sin n pi x by l would be b n plus b n star. So, we are getting this new Fourier series for f1 plus f2. Moreover, if the Fourier coefficient of the function of the CF, where C is a constant, or the C times the corresponding Fourier coefficient of f, that is, if my Fourier series for the function fx is a naught plus summation n is running from 1 to infinity, a n cos n pi x by l plus b n sin n pi x by l, then the Fourier series for the function CF would be given as C times a naught plus summation n is running from 1 to infinity, C times a n cos n pi x by l plus C times b n sin n pi x by l. Now, we just see that is the example explaining these properties which we have got. First example is for rectangular pulse. Find the Fourier series of the function fx as 0 in minus pi to 0 and 2a from 0 to pi fx plus 2 pi is equal to fx. That is, this is a periodic function with period 2 pi. We have to find out the Fourier series for this. Of course, we can find out the Fourier series. We do know the method how to find out the Fourier coefficients and then evaluate it, but we will just use the properties we had learned. Let us see. We have done in the last lecture one example where we had find out the Fourier series for this function minus a from minus pi to 0 and a from 0 to pi, and the periodic with period 2 pi. If you do remember, we have got the Fourier series for this function as 4a upon pi sin x plus 1 by 3 sin 3x minus plus 1 by 5 sin 5x and so on. And now we see that this my f, what we have got, this is nothing but so here in this one we are having is a naught and a n 0, and b n was 4a upon n pi for n odd and n even, and now this fx which we have to find out now the Fourier series, that is nothing but a plus f1x. f1x is minus a in 0 to pi minus pi to 0 and a from 0 to pi. So, if I add a, I would get 0 in minus pi to 0 and 2a from 0 to pi. So, we are getting this one. Now, we take f2 as a from minus pi to plus pi, and it is a periodic function with period 2 pi. As we know that constant function we can always treat with any period whatever we like. So, now For f1 we already know what is the Fourier series. For f2 let us find out the Fourier series. So, a naught star would be 1 upon 2 pi minus pi to plus pi a dx, that integral would turn out to be a. If I take a in star, that would be a upon pi minus pi to plus pi cos nx dx. We do know the integral minus pi to plus pi cos nx dx is 0 for all n integer n's. Similarly, the bn star would be a upon pi integral minus pi to plus pi sin nx dx. Again we know the integral minus pi to plus pi sin nx dx for any integer n is 0. So, we are getting both a n star and bn star as 0 for all n, and we are getting a naught star as a. So, the Fourier series for f2 is nothing but a, only the constant. So, now what we will get the Fourier series for f? Fourier series for f, that we would have that the coefficients of f2 and coefficients of f1, that has to be added up. So, what we will get the Fourier series a plus 4a upon pi sin x plus 1 by 3 sin 3x plus 1 by 5 sin 5x and so on. So, now you see that is using this property of the sum of the functions we can find out the Fourier series very easily. Now, let us do one more example. Find the Fourier series of the function f(x) is equal to x plus pi minus pi to plus pi and periodic with f(x) plus 2 pi as f(x). We have to find out the Fourier series for this function. Now, see, we had already done one more example in the last lecture where we had find out the function f(x) is equal to x for minus pi to plus pi and periodic with period 2 pi. So, now if we see my new function f(x) is nothing but f1x plus pi, and for this series f1x we do find out that the Fourier series was 2 times sin x minus 1 by 2 sin 2x plus 1 by 3 sin 3x and so on. That says is we have got a naught as 0, a n as 0 and b n as 2 upon n minus 1 to the power n plus 1 for n is equal to 1 to 3 and so on. So, now we have to just find out the Fourier series pi. f(x) is f1x plus pi. In the last example just now we had seen when this another function was just a constant, we have got that the Fourier series is nothing but that constant only. So, the required Fourier series would be now f(x) as pi plus 2 times sin x minus 1 by 2 sin 2x plus 1 by 3 sin 3x and so on. So, now we see is that is rather than finding out the Fourier series new, that is finding out all the Fourier coefficients again doing with the integrals and so on, we can try and we can do it by known Fourier series. We can just add up the constants or the Fourier coefficients and we can find out these Fourier series. These are the certain examples which are very easy we have done, but if you see is that we had find out for the two functions the Fourier series where the coefficients, finding the coefficients we have done the tough integrals. So, for the sum function or if the coefficients are also involved, we can find out the sum function or the linear combination by the just taking the linear combination of those Fourier coefficients. Let us go with this even and odd function. Now, we will come to one more practical problems which we are facing. Now, we had learned that Fourier series we can obtain for the periodic functions. That is, my function has to be defined on all whole real line and it should repeat after some time, that is the period. Now, most practical problems we do not have this kind of functions. We may have the functions which are defined only on a particular interval only, not on the whole real line. How to find out the Fourier series for that? How to solve those problems? We can do it. We can, what we do, we had learned, that is when we are finding out the Fourier sine series and cosine series, we are assuming is that if the function is even, we would get the Fourier sine series only. When the function is even, we will get the Fourier cosine series only, and the coefficients would be a naught as 1 upon L 0 to L f(x) dx and n as 2 upon L 0 to L f(x) cos n pi x by L dx for n is 1, 2, 3 and so on. Or if the function is odd, we can get the Fourier sine series with the coefficients Bn as 2 by L 0 to L fx sin n pi x by L dx. That says is we can find out the Fourier coefficients only for the function defined in interval 0 to L, but the condition is that the function has to be either even or odd and it has to be periodic. That says is that gives us an insight that for the function which is defined only on the interval 0 to L, for that also we can find out the Fourier series. The only thing is we have to either extend the function to the as even extension or odd extension. Let us see what we are meaning by these extensions. The function is, let us say, is defined only in the interval 0 to L here as this straight line. I can have its even extension, that is I can extend it to this, it should have the similar kind of function on the negative side also. Now I can repeat this function from minus L to plus L again, and that would be a periodic. Similarly, we can get the odd extension. We are having this function 0 to L, this was defined over as a straight line. For this we would just go with the negative one and we have this extension. Now we can go ahead with here again periodically like that one. So that says is that we can extend the function either even with even function or as an odd function, and then we can have the period as 2L, that is we can repeat it out. And now we are getting is even or odd function, and we can get the integral with the function defined only on 0 to L. Let us see how we are doing with the help of an example. This example says find the two half range expansions of the function fx, which is defined as 2k by L times x in the interval 0 to L by 2 and 2k upon L into L minus x in the interval L by 2 to L. We can see that this function is actually a triangle. We are having is that it is increasing in 0 to L by 2 and then it is decreasing from L by 2 to L. So, this is what is we are calling is triangle and its half range expansions. What is the meaning of this half range expansion? We have learned that is if the function is defined only in 0 to L, we will use the function only defined in the 0 to L, but what we will find out, either we will find out a cosine series or a sine series, that is either we will repeat the function 0 to L same as minus L to 0, that is as an even function, and then repeat it out, that is make it periodic function and find out the Fourier series, or make it as odd function from minus L to 0 and then repeat it and find out the Fourier sine series. So, whatever the series we are getting for this odd extension or even extensions, those things we are calling as half range expansions. So, let us try to see that is what is this function and what is it. So, the function is this triangle which is defined from 0 to 2. Let us first do the even extension, that is the function we have taken from 0 to 2, even extension, that is minus 2 to 0. I will repeat the same triangle over here. So, we see that the value at 0.5 is 0.5 here, value at minus 0.5 is also 0.5 here, value at 1 is 1 here. So, value at minus 1 is also 1, similarly value at 1.5 is 0.5 and value at minus 1.5 is also plus 0.5. That is we have just got this even extension, and now you see is that is it is a periodic function. So, we would just go ahead with this function now defined from minus 2 to plus 2, which is an even function, and we will repeat it. So, we can get the Fourier series. So, Fourier series, first we are doing this even periodic extension, we will get the what we will call this Fourier cosine series half range expansion towards even periodic extension of the given function. So, we will get this series as a naught plus summation n is running from 1 to infinity a n cos n pi x by L with coefficient a naught as 1 by L 0 to L f x dx and a n as 2 by L 0 to L f x cos n pi x by L dx. Let us try to find it out for this given function. So, the function is defined in 0 to L, which is been broken up into two parts, 0 to L by 2 and L by 2 to L. So, first the integral a naught 1 by L 0 to L fx dx. So, 1 by L integral 0 to L, that we will break up into two parts, 0 to L by 2, there the function is 2k by L x dx, and from L by 2 to L the function was 2k by L into L minus x dx. Now, integrate it out, you will get this integral as k by L times x square, 2x integral is x square. Similarly, here we will get L times x, and this integral would be k by L times x square, and evaluated here it is 0 to L by 2, here it is L by 2 to L. So, just doing these calculations we get 1 by L times k by L into L square by 4 plus 2 k by L into L by 2 minus k by L square minus L square by 4, that is at 0 the function would be 0 for all the values, which after simplification comes out to be only k by 2. So, we have got a naught as k by 2. Now, what is a n? The integral is 2 by L integral 0 to L x time fx times cos n pi x by L dx. Now, the integral will again break into two parts, that is 0 to L by 2. The function is 2k by L into x and then multiply with cos n pi over L x, and the other one is that is from L by 2 to L, the function is L minus x 2k by L times L minus x cos n pi by L x dx. Again we are integrating it by parts, because we do have x times cos x time kind of function. We would get it 4k by L square integral 0 to L x cos n pi by L x dx plus L by 2 to L cos n pi x dl. That is what we have taken the integral L times cos n pi x, that would be 0, and we are just getting thus a n as 4k by L square L upon n pi x sin n pi over L x evaluated from 0 to L by 2 minus L upon n pi into 0 to L integral 0 to L by 2 sin n pi by L x dx. This is the first integral. The second integral would be L square upon n pi sin n pi over L x evaluated from L by 2 to L, and minus L by n pi x times sin n pi over L x, this evaluated from L by 2 to L, and the integral for this one would be that the second part plus L by 2 integral L by 2 to L sin n pi over L x dx. So, a n would be 4k upon L square into L square upon 2 n pi sin n pi by 2 plus L square upon n square pi square cos n pi over L x evaluated from 0 to L by 2 minus L square upon n pi sin n pi by 2 plus L square upon 2 n pi sin n pi by 2 minus L square upon n square pi square cos n pi over L x evaluated from L by 2 to L, which would be 4k upon L square into L square upon n square into pi square, since n pi by sin n pi by 2 here would be 0. So, L square upon n square pi square plus into cos n pi by 2 minus cosine 0 minus cosine n pi plus cosine n pi by 2, which is coming as minus 4k upon n square into pi square times 1 plus cos n pi minus 2 times cosine n pi by 2. We can rewrite it again as a n as 4k upon n square pi square into 2 cos n pi by 2 minus cos n pi minus 1. Since n pi by 2 is 0 and cos n pi is plus minus 1 to the power n, we would get a n as 0 for n odd, and when n is even and it is of the form 2m with m as 2, 4 and so on, that is n is equal to 4, 8 and so on, it would be 0. when n is even and of the form n is equal to 2m with m as 1, 3, that is n is equal to 2, 6, 10 and so on, we will get an as minus 16k upon 4m square times pi. We can rewrite it again, since for all odd n an is 0, for even n, that is n is equal to 2m, we can write it as minus 4k upon m square pi square, for m taking values 1, 3, 5 and so on, that is odd values, and 0 when m is taking even values 2, 4 and 6. What it says is that my a1 would be 0, a2 when m is 1 will give me minus 4k upon pi square, then a3 being odd is 0, a4 is m is 2, that would be 0, a5 again odd is 0, a6 we would get as m is equal to 3 minus 4k upon 3 square pi square and so on. a10 we will get minus 4k upon 5 square pi square. Thus what we will get our Fourier cosine series as k by 2, that is what is a naught, minus 4k upon pi square cos 2 pi by L x. This 4k upon pi square with minus sign, this is common with all the coefficients, so that we have taken common. a1 is 0, a2 we are getting, a2 means n is 2, that is cos n pi x over L, that is so n is 2 here. Then the next term we would get is n as 6, so cos 6 pi x over L 1 upon 3 square and so on, we will get plus 1 upon 5 square cos 10 pi over L x and so on. Now the function we have taken as defined from 0 to L, with k one constant and L is another constant. In the example, the graph of the function which I had shown, I have taken L as 2 and k as 1. In that case, what I will get this Fourier series as k by 2 minus 4k upon pi square cos 2 pi by 2x plus 1 by 3 square cos 6 pi by 2x and so on, or we will get k by 2 minus 4k upon pi square cos pi x plus 1 by 3 square cos 3 pi x plus 1 by 5 square cos 5 pi x and so on. Moreover, we can keep k as 1, so I will get here 1 by 2 and here 4 upon pi square. Let us see the function and the Fourier series. So the function I have taken, L I have taken as 2 and k I have taken as 1. So the function is this triangle with the height 1 and this base as 0 to 2. We have taken its even extension, so we have taken this minus 2 to plus 2. For this periodic function, if the Fourier series and just whatever I have find it out, if I am just plotting it, it's just you see is that overlapping with this one, with this pink line is the Fourier series. The only point is where it is having a gap at is the peak at that one point, that is where it is changing the shape of the function. At that point we are having this little bit off of the function. So we are getting the Fourier series for the even extension of the function which was defined only from 0 to L. Now let us move to the odd extension. The function was defined from 0 to L as a triangle. Odd extension means is I have to take minus L to 0, the function value f of minus x should be minus of f of x. That is whatever value here we are having positive, in this side that I have to have that value as negative. So that means this has been inverted over here. So you see at 1 the value of the function was 1, while at minus 1 I require it to be minus 1. At 0.5 the value of the function was 0.5, at minus 0.5 I require it to be minus 0.5 and so on. So this is what is our odd extension with the function minus L to plus L, and then we can extend it as, make it as a periodic function. So this is odd periodic extension. Find out its half range expansion. This would be, because the function is odd, it should be Fourier sine series, that is I would get the series of the form n is running from summation n is running from 1 to infinity bn sin n pi x over L, with bn as 2 upon L 0 to L fx sin n pi x over L dx. So evaluate for our function what is my bn, that would be 2 by L 2k by L integral 0 to L by 2 x sin n pi x by L dx, since our function is defined from 0 to L by 2 and then L by 2 to L. So, the next integral would be 2k by L integral from L by 2 to L minus x sin n pi x dx. Now, evaluate these integrals. Wherever we are having this function x sin x, we would go for integral by part. This second integral we can break again into two integral, one integral with L times sin n pi and another integral minus x times sin n pi x. So, the second integral will again go by parts. So, Bn would be 4k upon L square L x upon n pi cos n pi x by L evaluated from 0 to L by 2 plus L upon n pi 0 to L by 2 cos n pi over L x dx minus L times L upon n pi cos n pi x over L evaluated from L by 2 to L plus L upon n pi x cos n pi x over L by 2 to L evaluation minus L upon n pi integral L by 2 to L cos n pi over L x dx. 4k upon L square into minus L square upon 2 n pi cos n pi by 2 plus L square upon n square pi square sin n pi x by L evaluated from 0 to L by 2 minus L square upon n pi cos n pi plus L square upon n pi cos n pi by 2 plus L square upon n pi cos n pi minus L square upon 2 n pi cos n pi by 2 minus L square upon n square pi square sin n pi x by L evaluated from L to L by 2. Now, do all the evaluation and we get Bn as 4k upon L square minus L square upon n square pi square into sin n pi by 2 minus sin n pi plus sin n pi by 2. Now, since sin n pi is 0, sin n pi by 2 we would get twice sin n pi by 2, that is 8k upon n square pi square sin n pi by 2, which says is for n odd it would be plus or minus 1, for n even it would be 0. So, B2m would be 0 for m is equal to 1, 2 and so on, and B2m plus 1 would be for 8k upon 2m plus 1 is whole square pi square into minus 1 to the power m, for m is taking values 0, 1, 2 and so on. That is what we have got, that B1 would be 8k upon pi square, B3 would be minus 8k upon 3 square pi square, B5 would be 8k upon 5 square pi square. That is, we are alternately changing the sign and getting the values, that is n square pi square downwards and in the denominator, and in the numerator 8k is common and we are alternately changing the sign. For the odd ones, for the even ones it is 0. So, what we will get the Fourier series as 8k upon pi square sin n pi by L minus 1 by 3 square sin 3 pi by Lx plus 1 by 5 square sin 5 pi by Lx and minus and so on. Now, in our example I have taken L as to be 2. So, I will get it actually 8k upon pi square sin n pi by 2 minus 1 by 3 square sin 3 pi by 2 x, of course here also is x, 1 by 5 square sin 5 pi by 2 x and so on. Let us see that is how it is approximating the function. So, this is what was our odd extension from minus L to plus L. Now, this is the Fourier series, this we have got with the sine function, this is one. Now, we are seeing is that this is not that much nicely approximating the function. Some of things are of course too far, because I have taken a small number of functions or small number of terms, but still we are getting is it's far away, or that even extension we were getting much nicer kind of approximation rather than this one. Let us see one more example what is happening. So, see, find the half range expansion for the function f(x) is equal to x, which is defined from 0 to 1 only. Now, the function is defined from 0 to 1. So, L is 1 here and the function is a straight line from 0 to 1. What we have to find out? The half range expansion, that is both even and odd extension. So, let us first say what will be this even and odd extension of this function. The function is defined 0 to 1 is a straight line. If I just go for the even extension, I'll have to have the same kind of line on the negative side, that is when x is 0.5, the function value should be 0.5 plus 0.5. So, when x is minus 0.5, the value of the function at minus 0.5 should also be plus 0.5. Value at 1 is 1. So, value at minus 1 should also be 1. So, we are getting is that this line is that original 0 to 1 fx. Here I have made this even extension. So, this is the similar kind of thing. Then we are making it periodic. Periodic means is that is now from minus 1 to plus 1 with the period 2. So, from 1 if it is repeating to 2, it should be repeating this function, that is from minus 1 to 0. So, we are getting this one. Similarly, here this repetition has to be from 0 to 1. So, we are getting is this is looking like a triangle, but actually this is extension is only this one, and then the periodicity is changing out, that repeating the values. Odd extension, the function was 0 to 1, then I have to make it odd one, that is whenever f of x is positive, then f of minus x has to be minus of f of x, that is negative. So, you see the value at 0.5 we are getting is plus 0.5. So, at minus 0.5 I should have the value as minus 0.5, that is this side. Similarly, at any point, so here we are having this point, say at 1 the value is plus 1. So, at minus 1 the value should be minus 1. So, we are getting is that this is the original function 0 to 1 and this is its odd extension. Again, for periodicity, if I am repeating the function from minus 1 to plus 1, again from 1 to 2 if I am repeating, it should have minus 1 to 0, that is the same function. Similarly, if it is repeating from minus 1 to 2, it should have been same as 0 to 1. So, minus 2 to 1, this is again repeating the same function. So, this is the periodicity, these ones. This is the extension in the interval minus 1 to plus 1. Let us see its half range expansions. So, for even extension, I want this kind of Fourier series, that is half range expansion Fourier cosine series only. A naught plus summation n is running from 1 to infinity a n cos n pi x. Since L is here 1, so I will not be getting n pi x over L, L is 1, so I would be getting it n pi x only. Find out what are these coefficients a naught and a1. A naught should be integral 0 to 1 fx dx and a n should be 2 times integral 0 to 1 fx cos n pi x dx. So, with the given function fx as x with the interval 0 to 1, evaluate it. A naught would be 0 to 1 x dx integral, that is half, and a n would be 2 times 0 to 1 x cos n pi x dx. Evaluate this integral by parts. You get 2x by n pi sin n pi x evaluated at from 0 to 1 minus 2 upon n pi 0 to 1 sin n pi x dx, because this is the first function and its derivative is 1 and this is the second function, its integral is sin n pi x upon n pi. Evaluate it, we will get it 2 upon n square pi square, since at x is equal to 1 sin n pi is 0, at x is equal to 0 sin 0 is 0. So, this term is not giving me anything. Here again this integral, so minus sin n pi x, its integral is cos n pi over n cos n pi x over n pi. So, we are getting is 2 upon n square pi square cos n pi x evaluated from 0 to 1. At x is equal to 1 it will be cos n pi, at x is equal to 0 it will be cos 0. So, what we would be getting is 2 upon n square pi square cos n pi minus 1. The value of cos n pi is minus 1 to the power n. So, we are getting is 2 upon n square pi square minus 1 to the power n minus 1. It says is a n we would be getting is for odd n minus 4 upon n square pi square, and for even n it would be 0. So, what will be our Fourier series? A1 would be minus 4 upon pi square, a3 would be minus 4 upon 3 square pi square and so on. Fx a0 we have got as 1, 4 upon pi square is common, so we are getting is 4 upon pi square cos pi x plus 1 by 3 square cos 3 pi x plus 1 upon 5 square cos 5 pi x and so on. This is the Fourier series. Let us see how it is making the even extension. This is the even extension 0 to 1 and this even extension over here. When we are plotting the Fourier series over here, we are finding it out that it is at the points where it is changing the values, that is at 0, at 1 and minus 1, we are getting is a little bit distraction from that, or this is not exactly matching over here, but here it is quite nicely overlapping one. Let us move to the odd extension and its half range expansion. We want fx as of the form bn sin n pi x, where bn would be 2 times 0 to 1 fx sin n pi x. Hence, evaluate this fx is x for the whole interval 0 to 1. So, bn would be 2 times 0 to 1 x sin n pi x dx. Again evaluate this integral with by parts. So, this integral would be minus 2 x upon n pi cos n pi x 0 to 1 plus 2 upon n pi 0 to 1 cos n pi x dx, because the derivative of x is 1. Here when I am putting x is equal to 1, I will get cos n pi and 1, and when x is equal to 0, this will give me 0. So, we would be getting is minus 2 upon n pi cos n pi plus this integral is sin n pi x over n pi. So, we will get 2 upon n square pi square sin n pi x 0 to 1. When x is equal to 1, we will get sin n pi. When x is equal to 0, we will get sin 0. Both values are 0. So, we are not getting anything from here, it will give only 0. We are getting it minus 2 upon n pi cos n pi. The value of cos n pi is minus 1 to the power n. So, minus 2 upon n pi minus 1 to the power n. This minus sign we are just joining over here. So, we get bn as 2 upon n pi minus 1 to the power n plus 1. Thus, the Fourier series we would get as 2 upon pi sin pi x minus half sin 2 pi x plus 1 by 3 sin 3 pi x and so on. Let us see how it is in the graph, how it is approximating the function. This is what is our odd extension, and the Fourier series just this sine series which we have find it out, that is this one. Now, you see here also we are distracting one, but the point is that is when we are ending up both the sides, the function as such, the function was here, and if we see the periodic function from here again we are starting in this manner, that is this has to go like this one. What it says is at the point 1, if I take the periodic function, the function discontinuous, that is if at 1 would be here from the left when we are reaching, it was reaching to the plus 1, when from the right we are reaching, it is reaching to the minus 1, that is it is discontinuous over here, and that is what we are getting is our Fourier series is just going down. If you have seen in the examples where we had find out the Fourier series where the function of this kind, and we are getting is that the values are distracted one. So, we are getting the Fourier series, we are functions we are getting like that one, of course the points are less, but it was joining one. So, that is what we are seeing is it is joining over here. So, this is what is our odd extension. So, this is what we had learned today. If the function is having certain properties, that is even or odd, we get either Fourier cosine series or Fourier sine series. Moreover, for finding out the coefficients, we are evaluating the integrals only on the half of the period, that is if the period is from minus L to plus L, we are evaluating it only all the integrals from 0 to L. So, when it is even function, we are evaluating the integrals for a0 and an, that is the coefficients of the cosine function, and we get Fourier cosine series. When the function is odd, we are getting only Fourier sine series, and the coefficients Bn, again we are evaluating the integrals from 0 to L, that is the half period only, rather than minus L to plus L. This property, and one more property we had learned, that is if we are adding the functions or we are taking a linear combination of any two functions for which we can find out the Fourier series, then the Fourier series of that linear combination of those functions can be just given as the linear combination of the Fourier series itself. From these two properties and the property of this even and odd functions, that has given insight to us that we can use this Fourier series for the functions which are not periodic, and they are defined only on some interval of the form 0 to L. What we have done is we had extended them either to the even extension or to the odd extension, that is the function which is defined from 0 to L only, we have made it from minus L to plus L, either taking the function from minus L to 0 as the same function from 0 to L, that is f of x as same as f of minus x, or we have taken an odd extension, that is taking f of minus x as minus of f of x, and then we repeated it from minus L to plus L, made it periodic with period 2L. Then we can find out the Fourier series for this extended functions, and we called it half range expansions. Our aim was actually to find out the Fourier series for the function which is defined only for 0 to L, but since the method we are knowing is defined for the periodic functions which is defined on the complete real line. So, we made it periodic by extending it from minus L to plus L, either making the function to be even or making the function to the odd, so that we are getting the integrals or the evaluation of the coefficient, the integrals we are using for 0 to L only, that is the given function only, which where it is defined from 0 to L. And we had seen that we are in our two examples, of course, both the times we had found it out that the even extension was much nicer looking in the graphs, while rather than the odd. That is because of that particular examples which we have taken, they were discontinuous at the end points, and then Fourier sine series was just going down like that because of the graphs which we have drawn like that one. But we have got that we can make it from 0 to L. Next we will see is, that is whenever we are finding it out that the graph is matching with the function or graph is not matching with the function, what is this properties, what is the value of the function at that particular point, value of, because we have started the Fourier series where we want the integral over an interval to be approximated by a series. So, next lecture we will see something more about the Fourier series. For today, that is all. Thank you.